All right, welcome back to the deep dive. Today we're going deep inside, like way down into how medications actually work in the body.
hmm
It's fascinating stuff. We're talking about pharmacokinetics, or PK for short.
Yeah, PK. Basically what your body does to a drug.
Right. It's like the drug's adventure through you. And to really break it down, we're focusing on these four key steps: absorption, distribution, metabolism, and excretion, or ADME.
ADME, yep. The core of PK.
Exactly. And by the end of this deep dive, you'll understand ADME like the back of your hand and see why it matters so much for drug safety and effectiveness.
Because it's not just about taking a pill, right?
No.
It's about what happens after you take that pill inside you.
Absolutely. So first up is absorption. Think of this as the drug's journey from, let's say, your stomach, if you swallow a pill, to your bloodstream.
The first hurdle. Got to get into the system.
Right. And a key concept here is bioavailability. You've probably heard that term. So imagine a pill has 100 milligrams of the active drug, the stuff that actually makes it work. Bioavailability tells you what percent of that 100 milligrams actually gets into your blood unchanged. And to really illustrate this, think about IV medications given straight into a vein.
Right. Like in a hospital setting.
Yeah, their bioavailability is 100%. All of it goes straight into circulation.
Makes sense. But pills, well, it's a different story.
Exactly. If you take that same 100 milligram pill orally, the amount that reaches your blood might be way less.
Way less. And so many factors at play. Like how you took it is a big one. Oral versus IV, like we said.
Mhm.
Then there's the drug itself.
Yeah, like its properties. Is it attracted to fat or
Oh,
water?
exactly. Lipophilic versus hydrophilic. Huge impact on how easily it crosses those cell membranes.
Right, because membranes are fatty.
Yeah, so a fat-loving drug slips right through.
Interesting. And then there's your body, right? How fast your stomach empties, blood flow in your gut. All that can make a difference in how much is absorbed.
Oh, for sure. Huge variations between people.
And then we have this fascinating thing called first pass metabolism.
Ah, the liver's grand entrance.
Right. So you swallow a drug, it gets absorbed by your gut, and before it can party in your bloodstream, it goes straight to the liver.
Liver's like the security checkpoint, checking IDs.
And the liver, or even the gut wall, can start breaking down the drug before it even reaches the rest of your body.
Yep. This first pass can seriously reduce how much active drug is left to do its job. Some drugs get hit hard.
So that bioavailability we talked about, it's significantly affected by this first pass.
Oh, absolutely. Key player in the whole game.
Okay, so let's say our drug made it through absorption. Now it's on to distribution.
Round two, spreading the love.
Yeah. This is where the drug goes from the blood into your tissues, your organs, everywhere. And blood flow is a major factor here.
Totally. Organs with lots of blood flow, like the brain, liver, kidneys, they get the drug faster. VIP access.
Makes sense. And then there's protein binding. You know how some drugs hitch a ride on proteins in your blood?
The protein taxis.
Right, but only the unbound drug can actually get off the taxi and do its thing at the target.
Yep. Got to be free to work.
Yeah.
And if a drug is really stuck to its protein taxi, well, less of it is available to work.
And what's even more wild is if two drugs want the same taxi seat, they can compete. Like, who gets the ride?
Drug interactions, uh-oh.
Exactly. And then we have tissue permeability, like how easily a drug can actually get into the tissues.
Yeah, like crossing borders. Some drugs have the right passport, others don't.
And the blood-brain barrier is like super strict customs.
Oh yeah, the brain's got its own security detail.
Yeah,
Tough to get in.
really keeps things safe up there. And then we have volume of distribution, or V.
VV, the drug's playground, essentially.
Right. It's like the apparent space in your body that the drug can occupy. High V'd, it's all over the place.
Party animal drug, low
Uh-huh.
V'd. It likes to hang out in the blood mostly.
Got it. Okay, so our drug is distributed. Now, what happens? Metabolism.
Ah, the transformation zone.
Mainly in the liver. This is where your body chemically changes the drug.
Making it easier to get rid of. Think of it like putting a handle on a slippery package. Easier to grab.
Interesting analogy. And the liver does this to make the drug more water soluble so your kidneys can excrete it.
Exactly. But sometimes metabolism activates a drug. It's like a secret agent getting their mission instructions.
Pro-drugs. They need to be metabolized to work.
Yep. Sneaky little thing.
So metabolism happens in two phases. Right?
Generally, yeah. Phase I is like roughing it up. Enzymes, especially these things called CYP enzymes, they add or expose reactive groups on the drug.
CYP enzymes, those are important.
Oh, super important. And then phase two is like attaching a shipping label. It's called conjugation, adding these big water-soluble molecules to the drug.
Makes sense. So liver function is key here.
Oh, definitely. If your liver isn't happy, drug metabolism can go haywire.
Right. And we all have slightly different CYP enzymes thanks to genetics.
Individualized medicine right there. Some folks metabolize drugs faster, others slower.
And some drugs can mess with these CYP enzymes, either speeding them up or slowing them down.
Drug interactions galore. Another reason why taking multiple medications can get tricky.
Absolutely. Okay, last step of our ADME journey, excretion. This is where the drug and its metabolites, those broken down pieces, leave your body.
By drug.
And for most drugs, it's mainly through your kidneys.
The kidneys are champs. Filtering your blood, getting rid of all the waste, including those water-soluble drug bits, out they go in the urine.
And sometimes drugs can be actively pumped into the kidney tubules or even reabsorbed back into the blood.
Yep, it's not a one-way street.
Fascinating. So kidney function, super important. If your kidneys aren't working well, doctors got to adjust drug doses carefully.
For sure. And while kidneys are the MVPs, other routes exist. Liver can excrete some drugs into the bile, which goes out in poop.
Right. And some drugs, like gases, that can be exhaled by the lungs.
Yep. And tiny amounts can even sneak out in breast milk or sweat.
So we've covered the whole ADME process. It's a wild ride. But to really bring it home, we need to mention some key pharmacokinetic parameters. We've already touched on bioavailability, volume of distribution.
The drug's resume, basically.
Right. So there's also clearance, or CL. It tells you how efficiently your body gets rid of the drug, like the volume of plasma cleared per unit of time.
Yep. Think of it like how fast you can clean your room. Some folks are quick, others take their time.
Great analogy. And then there's half-life, or T. This is the time it takes for the drug concentration in your blood to decrease by half.
The drug's fade-out time. Important for figuring out how often you need to take a medication.
Exactly. And finally, the area under the curve, or AUC. This gives us a measure of your total exposure to the drug over time.
It's like the total amount of sunlight a plant gets during the day impacts how it grows.
That makes sense. So these parameters, they help us understand and predict how your body handles a drug. Crucial for drug development and dosing.
Yeah, the foundation of personalized medicine. Making sure the right drug at the right dose gets to the right place at the right time.
So there you have it, ADME, the amazing adventure of a drug inside you. Understanding this is key for safe and effective drug use, and it shapes how new drugs are developed.
And think about this. Your genes, your health, all these things can dramatically affect these ADME processes.
So the same drug can have very different effects on different people.
It's like each of us has a unique map for how drugs travel through our body. Makes medicine incredibly complex and fascinating.
Absolutely. Well, that's it for today's deep dive. See you next time.